Okay, so these are some review problems for a multivariable calculus or a calculus 3 exam. This exam deals with multiple integration is the main focus. Okay, first question. We want to integrate a double integral from 0 to 2. On y bounds go from 0 to 2. X bounds from y squared to 4. And we're going to integrate square root 1 plus x to the 3 halves. Now, the initial thought I have is we can just integrate this square root 1 plus x to the 3 halves with respect to x. Problem is, that's a difficult antiderivative. So when you see this, one thing you can do is change the order of integration. I can integrate square root 1 plus x to 3 halves with respect to y, because this square root 1 plus x to 3 halves is just a constant. So it's y times the square root here. And then I'm going to hope that once I do that, it makes the integral with the x, sort of integration with respect to x, be much simpler. So I'm going to switch my order of integration. To do that, I'm going to graph out sort of my region here. So y goes from 0 to 2. My y bounds are 0 to 2. X bounds go from y squared to 4. So what that's going to look like here, I'm going to go y, let me draw this a little differently here. Y goes 0 to 2, so I only really need positive y's, 0 to 2. X goes from, extend this out further, out to 1, 2, 3, 4, and is bounded by x, well, is greater than or equal to y squared. So x equals y squared. Here, that's going to be sort of a graph like this. So that's x equals y squared. I mean, technically, we get a parabola with a half down here. Because we only have positive y's, this half doesn't really matter. And then x goes between y squared, this graph, and 4, which is this line here. And then this point of intersection happens to be the point 4, 2. X is 4, y is 2. Y goes from 0 to 2. And our region then is sort of this area here. So that's what we have. So what I want to do is rewrite this integral as a dy dx integral. So we need bounds. We get square root 1 plus x to the 3 halves. And then we're going to get this as dy dx. And now what I'm going to think about is x goes from 0 up to 4. So that's my x bound. And then the y bounds here, I'm going to think about if I fix an x, say here, really my y goes from there to there. So I get this sort of rectangle. The bottom bound, that's y equals 0. So I get 0 as my bottom y bound. The top bound is this function here, and that's y. Well, I have to solve for y. It's x equals y squared, but if I solve for y, that's y equals square root of x. Note it's the positive square root here. Down here would be negative square root of x, but that's not really part of our region that we're concerned about. So y goes up to square root x. So I change my order of integration. This is no guarantee this is going to work, but at least I can do the first integral now. And so when I do that, what I'm going to get is an integral from 0 to 4. I get y times the square root 1 plus x to the 3 halves. Again, when I integrate with respect to y, this square root is just a constant, so I get the constant times y. And my bounds go from y equals 0 up to y equals square root x. Okay, so what I get is integral 0 to 4. When I plug in square root x for y, I get square root x times square root 1 plus x to the 3 halves. And when I plug in y equals 0, I'm going to get a minus 0 here, which doesn't really matter. So if I plug in y equals 0, I get a 0 times something is just 0. Okay, now this, let's just rewrite this. I'm trying to integrate 0 to 4. I have x to the 1 half, square root x is x to the 1 half, times 1 plus x to the 3 halves, all to the 1 half. Now, what I can do here is I can now let u be 1 plus x to the 3 halves, this inside of this square root, sort of the bigger square root, and then du is 3 halves x to the 1 half dx. Note this x to the 1 half I now have outside of here because that came from my y. So I'm actually going to be able to integrate this. I need to get a 3 halves x to the 1 half. So what I can get is a 2/3 on the outside times 3 halves x to the 1 half. So the 2/3 times 3 halves would cancel, but I need that 3 halves to fit here. And I get 1 plus x to the 3 halves to the 1 half dx. And so now I can integrate and get 2/3 times 1 plus x to the 3 halves to the 3 halves divided by 3 halves. So this is now sort of a u to the 1 half integrates to u to the 3 halves over 3 halves. And I get this from x equals 0 to x equals 4. Okay, so let's evaluate this expression here, plugging in x equals 4, x equals 0. So what I get here is I get 2/3. Let's see, this 3 halves is going to come to the top as a 2/3. 2 times 2 is 4, 3 times 3 is 9. And then I have to evaluate 1 plus x to the 3 halves at x equals 4, 1 plus x to the 3 halves to the 3 halves at x equals 4, and then the same thing at x equals 0. So when I plug in x equals 4, I get 1 plus 4 to the 3 halves minus 1 plus 0 to the 3 halves to the 3 halves. And what I get now is 4/9. Let's see. 4/9 to the 3 halves. So 4 to the 1 half, that'd be square root of 4. That's 2 cubed. So I get 1 plus 8. That's 9 to the 3 halves. Minus 1 plus 0 to the 3 halves is 0. 9 minus 1 to the 3 halves. And so what I get is 4/9 times, let's keep this here. Let's see, square root of 9 with this to the 1 half is 3. 3 to the 3rd is 27. 1 to anything is 1. So I get 4 times 26 over 9. That's going to be 104 over 9. So there's our answer. Just a visual of what's going on with our region. I should have done this at the beginning probably, but this is our region. Here's a Mathematica plot of the region. Here I did sort of with both bounds. If you look up here in these sort of criteria here and here, you can see sort of both bounds. But you see I get sort of the same region here. And you can get that sort of a nicer picture than what I drew. But generally I think this is sort of sufficient. Next one. We want to evaluate the double integral over some region R of x over y with respect to area, where R is the region in the first quadrant bounded by y equals 1 over x, y equals 9 over x, y equals 4x, and y equals x. Okay, so what we can do here, let's just graph this. We're in the first quadrant. Y equals 1 over x, that's going to look something like this. So that's y equals 1 over x. Y equals 9 over x, the same thing, but sort of multiplied by 9. So that's going to scale out like this somehow. Probably not completely to scale, but gives you a sense of what's going on. I get the same kind of, I guess, hyperbola shape. Y equals 4x is aligned with slope 4. This is y equals 4x. And then I have y equals x, should be slope 1 plus slope. So our region is this area here. Now my first thought is set this up as a dx dy integral, but I run into some trouble here, because if I look at this as sort of doing, let's say, horizontal cross sections, I go from this function to this function, well, until I get to this point, and then I go from this function to that function, and then once I get to this point, I go from that function to that function. So I've got to find these intersection points. That's probably going to give me 3 integrals here, which in principle I should be able to do, but looks a little bit annoying. So let's try vertical cross sections. I'm going to sort of split this up, let's say, into one line here, another line there, and what I get is sort of this region on the left. I get sort of certain bounds here. On the right, I'll get some other bounds, in the middle. On the far right, I'll get some other bounds. So that seems like not what we want. So let's see if we can get rid of those. Well, it's going to be a little tricky. Yeah, again, the horizontal split is I'm going to do this bound and then a bound there, and I have sort of this top region, and then this middle region, and the bottom region, and they have sort of different left and right bounds here, or at least one of them switches in each one. So in principle, that would work. That's not what I'm going to do here. But let's just to make sure you have a sense of what's going on, let's look at a better picture here with Mathematica, drawing this sort of region to scale. There's sort of my y-axis, x-axis, here's the region. Again, I can't just go from this function to that function vertically. I can for a while, but then eventually I've got some other region here. So I've got to do something else. So what I'm going to do is I'm going to use a change of coordinates, and what I'm going to look at is I see y equals 9 over x, y equals 1 over x. I'm going to rewrite these as, let's see, y equals 9 over x. That's xy equals 9, y equals 1 over x. That's xy equals 1. And now I'm thinking I can make a variable be xy. So what I'm going to do is let's let u, so we're going to change of variables, we're going to change of coordinates, I suppose you could call this too. I'm going to let u be xy. So then what I have is u just goes from 1 to 9. So what I get is u goes from 1 to 9. It starts at u equals 1, is this graph here. This is u equals 9. So that's pretty slick. The other ones, I can do something similar, solve this for a constant. Y equals x, that would be y over x equals 1. Y equals 4x, that would be y over x equals 4. And so what I'm going to do is let v equal y over x, and then my line bounds really go from v equals 1 to v equals 4. So those are my bounds there. So that's my setup. In my new region, really easy to integrate. If I do this in the UV sort of plane here, u goes from 1 to 9, v goes from 1 to 4, and the region that I'm trying to integrate over is just this rectangle. So I just use these bounds. I'm going to get a really simple integral if I can do the change of coordinates reasonably. So I need to find a Jacobian and this kind of thing. So what I'm going to get is my integral over r. Let's see, it was either x over y or y over x. It was x over y that we're integrating. X over y dA. What we're going to get is we can rewrite this as a new integral. So I'm going to say sort of this region is r. Let's call this one, I don't know, for lack of a better term, let's just call this r2. That region. We can integrate over r2. And we're going to do x over y. So we got to figure out what x over y is. Well, v is y over x. So x over y, that's 1 over v. And we can really set this up as either a du dv or dv du. Let's just do du dv here. But what we need is our Jacobian. So some Jacobian, really absolute value of Jacobian, or maybe we'll just put that in there, Jacobian. So what we need here is our Jacobian. What we're going to do is that if, well, let's say it's, what do we get here? So our Jacobian, we could write it, so we have u, how do I want to say this? So if we're going to end up, if we started with uv and we ended up with xy, so our Jacobian, it's not really what we want, but if you do sort of a derivative of, let's see, we've got to do uv's and xy's. So if we did uv, started at uv, ended up at xy, what we would get is the determinant partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of v with respect to x, partial derivative of v with respect to y. Now this is really not the change of coordinates we want. This is the inverse change of coordinates. So we're going to get some answer here, but because we want this flipped over, this isn't the j we want. This is 1 over j. Here, so when you do an inverse, you get sort of the reciprocal of the determinant. So what we can do here is sort of do our partials this way and solve this out. So what you get here, partial u with respect to x, that's y. Partial u with respect to y, that's x, because u is xy. Partial v with respect to x, that's going to be negative y over x squared. And then partial v with respect to y is 1 over x. And we do a determinant, so we get y over x minus this times that. The negative is going to make that a plus. We'll get xy over x squared. And so this will give us y over x plus y over x. Whoops. Plus y over x. That's 2 times y over x. Now, but look, v is y over x. So that works out to be 2v. So our Jacobian, well, 1 over a Jacobian is 2v. So the actual Jacobian we want is 1 over 2v. Now, alternatively, instead of doing things with sort of reciprocal technique, is the standard thing is you would have to solve this system of equations pair, u equals xy, v equals y over x, for x and y. So in principle, you can do that. So if you wanted to do that, and you're just trying to get rid of this 1 over 2v out, so let's say we want to do u equals xy, v equals y over x. We want to solve for x and y. So let's maybe just work that down here. It's in red, maybe. So we have u equals xy, v equals y over x. I want to solve for x and y. let's see here. So what we could do, we could say maybe multiply both by x. Let's try that. So you get ux equals x. Well, no. Don't really need to do there. If I multiply this second one by x, what I'll get is xv equals y. And then I can get from the first one, if I know y is xv, u is x squared v. And so this tells me that x squared is u, whoops, okay, u. X squared is u over v, and that gives me x is square root u over v. Now it'd be plus or minus, but from our diagram and where we're working, we're in the first quadrant, we know x is positive. So we get a positive square root. So that's x in terms of u and v. And then v, let's see if we can do the same thing now. V should be, or sorry, not x, we need y. Y is x times v. So y is x times v, but x now is square root u over v times v. That's going to give me square root of uv. So v over square root of v is just square root of v. Now let's just work that out here. So this is square root of u over v times square root of v squared. We end up with square root of uv squared over v, which just gives me square root of uv. So I get y is square root of uv, x is u square root u over v. And then when I want to do my Jacobian here, what I really get is I get a derivative of xy sort of with respect to uv, and I get this partial derivative sort of determinant. I get a partial of x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v. So you work that out. X with respect to u, so here's x. That's going to give me a 1/2 derivative, so 1/2 times, let's see, 1 over square root of uv. So 1/2 this square root to the negative 1/2 times the derivative of the inside when I take it with respect to u, that's 1 over v. Partial x with respect to v, it's going to be 1/2 times, let's see, partial x with respect to v. We're going to get 1 over square root u over v again, this thing to the negative 1/2, and then the derivative of the inside is negative u over v squared, derivative with respect to v on the inside. Now the y's, partial with respect to u, is going to be 1/2, 1 over square root uv, times the derivative of the inside is v, and then with respect to v, I'm going to get 1/2, 1 over square root of uv times u. So I end up with this determinant, which looks uglier here. Let's see, I get this times that. What we're going to end up with, let's see, that's going to be a 1/4 times, let's see, we'll get a u on top. We'll get a, let's see, this square root v can go to the top, so we have a square root v on top. And we have a square root of uv, and it's u, so we get a v square root of uv times u there. And then minus this times that, but we have that negative, so we get a plus. 1/2 times 1/2 gives me a 1/4. Let's see, and then we get, let's see, we have a u on top, a v on top. This square root v will go on top, uv square root v. And then on the bottoms, we have a square root u, another square root u, that'll give me a u. That square root u, that square root of u. We have a v squared and a square root v. Okay, so we work that out, and now we got to simplify. Let's see, over here, let's see, square root v, this v on the inside, whoops, that didn't work very well. Let's do v on the inside. That v on the inside is going to cancel this square root v on top. The u and u multiplied together gives me a u under the square root, gives me a u on the outside. That'll cancel with that u. And so this first term is just 1 over 4v. Second one, see, when I do my cancelization, I get u's, v cancels with one of the v's on the outside, square root v's cancel. I get another 1 over 4v. You add these together, this is like 1/4 times 1 over v plus 1/4 times 1 over v. That's 1/2 times 1 over v. That's 1 over 2v, which is the same thing we got up here. So these match here. Point being, we did this two ways. You only really need to do one. The straightforward way that you'll find in sort of basically every book that does this is this, oh, solve for x and y, do these derivatives here. It works out here. But if you can know this inverse trick, things are just a lot simpler here. So I think this is worth knowing here. You get this sort of reciprocal inverse trick, and then you don't have to actually solve for x and y. Okay. In any case, you do this one way or the other. And what you get now is this integral here. So what we're going to get is the integral over R2. So we get an integral over R2. It was 1 over v was the thing we're integrating. Our Jacobian is 1 over 2v. And let's do this as a du dv integral. And then u and v, let's see. U goes from 1 to 9, v goes from 1 to 4. So u goes from 1 to 9, v goes from 1 to 4. And now this is a really straightforward integral. So I have a 1 to 4, 1 to 9. I have a 1 over 2v squared, du dv. So this is 1 to 4. I just get a 1 over 2v squared times u when I integrate with respect to u. From 1 to 9 dv. I'm going to get 9 minus 1, that's 8. So I'm going to get 8 over 2. I'm going to get 4 over v squared dv. And then when you integrate v to the negative 2, you're going to get, see, it's going to go to v to the negative 1. So you get a negative 4 over v. And your bounds are going to go from, let's see, v equals 1 to v equals, whoops, not u, v equals 4. And so what I'll get when I plug in 4, I'll get a negative 1 plus 4. That gives me an answer just of 3. So we're able to do this question. If you ignore the stuff in red, you could probably do this relatively quickly here with the Jacobian, although you might not sort of remember this inverse trick, and then you kind of have to do the stuff in red instead of this sort of section in blue up here. But either way works. Next one. Okay, so we're going to evaluate integral negative 3 to 3, then, well, negative 3 to 3 for x, and then y goes from 0 to square root 9 minus x squared, the function e to the x squared plus y squared. Okay, so again, the first thing I try and do with these is think, can I integrate this right away with respect to y? E to the x squared plus y squared. Let's see, when I look at that, I can split this up into e to the, well, no, I've got e to the x squared plus y squared. Let me just say this. I don't know how to integrate that with respect to y. So really, I don't really know what to do. I could do a u equals x squared plus y squared, but then I need like a y out in front to get a du or something. I don't know what to do. So that doesn't work out. So I'm going to start thinking of what I can do for tricks. I'm in the plane. I see x squared plus y squared. I see this square root here. This makes me think use polar coordinates. So let's graph out our region here. X goes from negative 3 to 3. Let's just write that down. Negative 3 to 3. X goes from negative 3 to 3. Y goes from 0 to square root 9 minus x squared. Now, this y, this upper bound is y equals square root 9 minus x squared. If you square both sides, you get y squared is 9 minus x squared. That's x squared plus y squared equals 9. That's a circle of radius 3. So what we get, if you think about this, is I go negative 1, 2, 3, positive 1, 2, 3, go 1, 2, 3 in the x direction. My region, I have this circle here of x squared plus y squared equals 9. My region, x goes from negative 3 to 3. Y just goes from 0 up to this. So what I get, really, my region is this semicircle, or, well, half disk, I guess, semi-disk. Filled in. Circle would just be the outside here, but it's filled in. So then again, this makes me think, oh, hey, that's going to be really easy to do in polar coordinates. So let's set this up in polar coordinates. What we get is an integral of e to the x squared plus y squared. So in polar coordinates, x squared plus y squared, that's r squared. We can do a dr d theta, and now you need a Jacobian. We could do the last problem where we could work out x equals r cos theta, x equals r sine theta, take that partial derivatives, get that determinant, calculate that out. It turns out that what you get all the time for polar coordinates is you just get an r. So we get an r dr d theta here. So this r, that'd be if you did the Jacobian calculation here. And now I just need bounds. theta, what does theta go from and to? Well, from this to here, this is theta equals 0, and I go up to theta equals pi. So theta goes 0 to pi. R starts at the origin and just sort of goes out to this circle, which is always 3. So this x squared plus y squared equals 9, in polar language, that's the equation r equals 3. So these are my bounds, and I get a somewhat nice integral here. The really big trick here is this e to the r squared. I picked up this r from the Jacobian, and now I can do a u equals r squared. So when I integrate this, what I get is 0 to pi. Maybe I should write out u equals r squared, du equals 2r dr. So I need a 2, so I get a 1/2. And then when I integrate e to the u, I get e to the u back, r squared. And then I go from r equals 0 to r equals 3 d theta. So an integral from 0 to pi, I get the 1/2. When I plug in 3, I get e to the 9th. 3 squared is 9. Minus when I plug in 0, I get e to the 0, but that's just 1. So I end up with this. And when I integrate this, this is a constant from 0 to pi. That's a rectangle whose height is 1/2 e to the 9th minus 1, whatever that is. And width is pi. So I'm just going to multiply by pi. Or you integrate and get a theta there. But what I'm going to get is this is pi over 2 times e to the 9th minus 1. Okay. Next question. Okay, we want to evaluate triple integral. We're in a dv integral. We're integrating the function x, where our region that we're integrating over is d, where d is the tetrahedron with vertices 0, 0, 0, 3, 0, 0, 0, 2, 0, 0, 0, 1. So when I draw this here, I just got to sort of get bounds for integration here. Let's think about this. So if I do x, y, z here, what I've got is, let's see, I've got a point at 3 out here. So maybe do 1, 2, 3. On the y-axis, I've got to get a point at 2, and on the z, I've got a point at 1. So I get a point here, I get a point here, point here. I'm not drawing these to scale, but these are, and then I get a point at the origin here. Now what I'm going to get is I'm going to be able to bound these 3, or put a plane through these 3 points, and that gives me a triangle, and then that tetrahedron is a sort of region inside. So let's see, I think I've got a Mathematica. I've got some drawings from other things here. Nope, don't have it, but that's okay. Yeah, don't have it. So this is sort of, it's a tetrahedron. I have 4 vertices. That's sort of what's going on. So what I need to do is set up bounds. Now it doesn't really matter because of the sort of symmetry in x, y, and z. I mean, these constants 3, 2, and 1 are different, but essentially there's nothing more complicated in x, y, and z. It doesn't really matter what order I want to do these in. I have these this x here. Sometimes I like to integrate that first. So let's just do this, triple integral x. Let's do dx, dy, dz. Maybe that's a mistake, but we'll do it this way. Might look at some other orders later on and see how things work out here. So now what I have to think about is z goes from 0 to 1. So I'm going to start on the outside. Whoops. Z goes from 0 to 1. And then y, okay, y goes from 0 to 2, but we've already fixed z. So once you fix z, you really get this triangle. This is kind of hard to draw in here, but you get a triangle cross-section. There, so you get that triangle cross-section. Well, let's just draw that out here. So let's draw this. Now we fixed z. We're now really in the xy plane. What we're going to get, here's this point here. Well, this point here. So I have a z coordinate. I don't know what x and y are. Well, I do know. Okay, wait. I know x is 0. So this is 0 something for y, and then I get z. This point here, let's see, that's x is 0, so I'm going to get a point up here. This point is really 0, comma, some y coordinate. Here, I don't really care about the z fixed in the plane. This point here in 3-dimensional space, x, I don't know what that is, y is 0, and then I get whatever z is. So that's going to give me a point in the plane of something, something comma 0. So maybe I should just leave that as something unknown comma 0. Maybe I should leave this one over here as something unknown as well. So I have to figure out what these things are. To do that, what I'm going to do is I'm going to look at the plane that includes my 3 points on the axes. So So this 3, 0, 0, 0, 2, 0, 0, 0, 1. So I want to get an equation for that plane. And then I'm going to use that equation where I can plug in z here, plug in x is 0, and then these coordinates here will have z's in it. So, okay, equation for that plane. What I'm going to do is, you could go through the standard procedure and find sort of two vectors, take their cross product, get a normal vector, use a point. That'll work out. But what's simpler is I can just look at these and see, well, the x, y's, and z's don't interact. The least common multiple of 6. So that plane, if I think about it, 2 times 3 gives me 6. So that's 2x. 3 times y gives me 6 plus 3y. 6 times z gives me 6 plus 6z equals 6. So the claim is this is the equation of the plane that includes 3, 0, 0, 0, 2, 0, 0, 0, 1. You can check that. If x is 0, y is 0, z is 1, I get 6. If x and z are 0 and y is 2, 3 times 2 gives me 6. If y and z are 0, x is 3, 2 times 3 gives me 6. So that certainly is the equation of the plane. So what I'm going to do now is I got to fill in these coordinates, which I haven't left enough space for, probably. But what I'm going to get here is this point there. It's on the plane, and that's when x is 0 and z is z. So when I do that, what I'm going to get is 3y plus 6z equals 6. And if you solve that, so you can divide by 3, y plus 2z equals 2. So I'll get y is 2 minus 2z. So the point that we get here, this point is 0, comma 2 minus 2z. Let's do this in blue. No, not blue. How about purple, I guess? This light. Let's try the light purple. Here, this other coordinate here. Well, that's when y is 0 and I have z. So when I plug in y equals 0 in the equation of the plane, I get the 3y to drop out. And I get 2x plus 6z equals 6. Can divide by 2, get x plus 3z equals 3. And so I get x is 3 minus 3z. So what we get here is this is 3 minus 3z. Okay, so those are my 2 points. And my region there, this sort of triangle, I'm looking for this, well, let's do it this way, this region here. I'm trying to find that region there. So this is y. So y is going to go from 0 to 2 minus 2z. I go to my bound. So I go 0 up to the top y. That's 2 minus 2z. And x is going to go from 0 up to whatever this line is. So I go 0, and it's going to go up to whatever this line is. Well, that line, I fixed y, and I've got a z fixed. Well, what I can do to find this upper bound is I take my plane equation, I just solve for x here. So I have 2x plus 3y plus 6z equals 6. What I could do here is y is going to go from here to here. Or sorry, no, y is fixed. X goes from here to here, so x starts at 0. I'm going to solve this for x. So I get 2x equals 6 minus 3y minus 6z. So x is 6 minus 3y minus 6z over 2. So I get 6 minus 3y minus 6z over 2. Okay, so that's the setup here. Again, the general strategy is we sort of just fixed a z. Once you fix a z, you get this triangle. That triangle gives me sort of the y bound goes from 0 to 2 minus 2z. Once I have y and z fixed, I can get x just by solving for my plane equation. Note, I did some work here, finding this 3 minus 3z and this point here. I didn't actually use that, but sometimes it's nice to see sort of how things work out. You could have gotten an equation for this line, I guess. That might have been something that would have worked out. Well, it would have worked out the same way with the plane. So you could have done that. It would have been more complicated, likely, or at least different. Okay, now I have to integrate this, which is a little bit annoying looking here. But let's go through this. So the first thing I'm going to get, I'm going to do the x integral. So I get an integral from 0 to 1, integral from 0 to 2 minus 2z. I get x squared over 2. And I have to go from x equals 0 to x equals 6 minus 3y minus 6z all over 2. And then I do this dy dz. Okay, so what I'm going to do, let's say I get 0 to 1. 0 to 2 minus 2z, I get a 1/2 out in front. So I get a 1/2 times, when I plug in this x and square this, I'm going to get a 6 minus 3y minus 6z squared. I'm going to divide by this 2 squared. That's going to give me a 4. When I plug in the x equals 0, I'm just going to get 0. So this is my bound here. Now what I'm going to get, let's just rewrite this. The 2 and the 4, I can get a 1/8 on the outside. 0 to 1, 0 to 2 minus 2z. That's my y bounds. And I have 6 minus 3y minus 6z squared dy dz. Now, one thing that I'm tempted to do is sort of FOIL out this square, multiply out this square, expand this. I guess FOIL doesn't work because it's a trinomial. But expand this out here and get something. I think it's going to be easier to sort of use a u substitution where you let u equal 6 minus 3y minus 6z. So when I do this, I'm going to get 1/8, keep my 0 to 1, and then when I integrate this, I'm going to get 6 minus 3y, 3 there, 6 minus 3y minus 6z cubed over 3. So this is like a u squared, but I really needed to have a, let's see, with respect to y, a negative 3 out in front. So to compensate for that, I get a negative 1/3. And then I'm going to integrate this from y equals 0 up to y equals 2 minus 2z. And I have to do dz. Okay, so I have 3 and 3. That's not 9 times 8. I get a 1 over 72. I'm going to leave that negative for the time being because I know sort of what's going to happen here. Whoops. So what I'm going to get is when I plug in y equals 2 minus 2z, I'm going to get 6 minus 3 times 2 minus 2z minus 6z cubed. And then I have to make sure I plug in the y equals 0. That's going to give me a minus 6 minus 6z cubed dz. And I've got that negative left inside, so I get a negative out in front here. Okay, so what happens in this part here is 6, I get, let's just do this in red here. I get 6 minus, when I distribute this, 6 plus 6z minus 6z. That whole thing goes to 0. So this first term just drops out. And then what I get is the negative and the negative give me a positive. I just get 6 minus 6z cubed. So if I do that, what I'm left with is an integral from 0 to 1, 6 minus 6z quantity cubed dz. And I'm going to integrate this. I get the 1 over 72. I get 6 minus 6z to the 4th over 4. But then the derivative of the inside was negative 6. So I should get a negative 1/6. And then if you integrate this from z, or evaluate this from z equals 0 to z equals 1. So what I get when I plug in the 1, let's see, I get 1 over 72 times 4 times 6. I'm not even going to multiply that out for now. I'm hoping something's going to simplify. What I get, let's see, when I plug it in, well, I get a negative here. Negative 1. When I plug in z equals 1, I get 6 minus 6, that's 0. Minus, when I plug in 0, I get negative 6 to the 4th. And so I get negative times negative. I end up with 6 to the 4th over 72 times 4 times 6. Now I just need to simplify this. And again, you could just multiply everything out and try and simplify or ask your calculator. This isn't really that bad. I can cancel this 6 on the bottom with one of the 6's here. I get 6 cubed. 72 is 2 times 36, which is 6 squared times 4. And then the 6 squared goes away, and I just have 6. It gives me 6 over 8, and gives me an answer of 3/4. So a little bit annoying to do going through, but sort of a straightforward question. Nice thing to be able to do here. Again, maybe I should have said I didn't emphasize this. This 6 minus 6z to the cubed, again, you could have expanded that out, but a lot of times keeping this factored when you've got a linear thing inside is sort of an easier calculation to do, by hand at least. Next one. I want to evaluate the triple integral over the region D, function y over dv, where d is the part of the cylinder x squared plus y squared equals 4, but this is in the first octant and below the graph of z equals square root 9x squared plus 9y squared. Okay, so what I'm going to think of here, I see a cylinder, x squared plus y squared, and then this z equals 9 really times the quantity x squared plus y squared. I see lots of x squared plus y squareds floating around. So what I'm going to do is I'm going to use cylindrical coordinates. I'm going to use cylindrical coordinates. And then the substitutions then are really that like x squared plus y squared equals r squared. Let's see, x is r cos theta, y is r, whoops, make that a better theta. We're at it. Y is r sine theta here. So those are, some of the things going on. What we're going to get then is a triple integral. That y is r sine theta times my Jacobian for cylindrical, same as polar, it's actually an r. So you get an r, and now I can do dr, d theta, dz. Doesn't matter a whole lot what the order is. It might be determined by the region. So let's think about this region. So z equals, let's just write down dr, d theta, dz. Let's see if that works out here. I don't know if it will or not quite yet. If you do this, so the region, basically I'm inside a cylinder. So this is x squared plus y squared equals 4. So in the xy plane, what I've got is really a circle. This is r equals 2. Square root of 4 is 2. So in the xy plane, I'm in the first quadrant, effectively. And then I've got above this some region that's bounded above by z equals square root 9x squared plus 9y squared. So let's figure out what that is. So if I do z equals square root 9x squared plus 9y squared, I could square both sides. I get z squared equals, well, 9 times the quantity x squared plus y squared. This gives me z squared equals 9r squared. And so essentially this is z is plus or minus 3r. We're really dealing with the positive one, so I probably don't really need the plus or minus. I could just do z equals, 3r. So if I graph this in sort of an RZ mode, this is a line. So it's something like this. Well, it should be a line through the origin. Now let's just start over. Okay, so if I graph this in the ZR plane, I get a line through the origin, something like that, and I'm going to basically rotate that around Z. That's going to give me a cone. So it's going to give me a cone, and it's just sort of the cone, part of the cone above this this quarter circle in the XY plane. So it's beneath the cone above this. So let's look at, I think I do have a Mathematica picture for this. So the drawing here, I think this is my setup here. So you've got here, so sort of this is the XY plane, first quadrant. You get that quarter circle, or quarter disc, I suppose. And then what you've got really is there's this cone top here. You can sort of see the cone here. There's a little bit of jaggedness. That's because of the way this is being drawn here. There's a little jaggedness at the top. Should be smooth. But there's a cone that sort of bounds this above. So it's like you took a cone, chopped down with a quarter cylinder, and you get this, I don't know, sort of wedge-shaped thing. Here. So what we're going to get here, now let's think about this. R, well, R is going to go from 0 out to 2. Now, I think this isn't going to work very well. Theta in the first quadrant goes 0 to pi over 2. Now here's why things aren't going to work. Z, what Z does is Z starts at 0. Here starts at 0, and it goes up to this function, really that cone we solved for, that's Z equals 3R. So Z goes from 0 to 3R, but that means really we have to have Z dz inside of dr for that to work here. So that's really our setup. So what I'm going to do, sort of forget this ordering for now, do an integral. I get the r times sine theta, r sine theta times r. That's r squared sine theta. I'm just going to make sure I do dz dr d theta. Dr d theta doesn't matter the order. I just need dz inside of dr here. And so what I get now is z goes from 0 to 3r. R goes from 0 to 2. Theta goes from 0 to pi over 2. And now I've got something I can actually integrate. Okay, so now it's just a matter of integrating. What we get, we're going to integrate r first. So you get integral 0 to pi over 2, integral 0 to 2. That r, so you have sine theta is sort of a constant in front. We get an r cubed over 3. Oh no, sorry, not r first. Z first. We're going to integrate z first. So we get really r squared sine theta as our constant. And then we get z from z equals 0 to z equals 3r. And get dr d theta. So we go 0 to pi over 2. 0 to 2. When you plug in 3r, you're just going to end up with 3r cubed sine theta. This equals 0 will go away. So now it's dr d theta. Now we can integrate with respect to r. Get an integral from 0 to pi over 2. We get 3r to the 4th over 4. R cubed goes to r to the 4th over 4. Keep the sine theta. We do r equals 0 to r equals 2 d theta. If we plug in r equals 0, this is going to go away. We'll get a 0, so we just need to worry about r equals 2. So we're going to end up with an integral from 0 to pi over 2. See, r squared is 16 over 4 is 4. 4 times 3, that's going to be 12 sine theta d theta. I'm just going to integrate to negative 12 cos theta from 0 to pi over 2. It's going to be negative 12 times cosine pi over 2 is 0. Cosine of 0 is 1. We get negative 12 times negative 1. That gives us an answer of 12. Okay. Last one, what we've got here is find the volume. So volume means we're going to do a triple integral of the function 1. So we're going to find a volume of the region in the first octant that is below z equals square root of something with x squared plus y squared. That's going to be a cone again. So it's below this cone. And between the spheres, x squared plus y squared plus z squared equals 4, and x squared plus y squared plus z squared equals 9. So when I see these two spheres, that makes me think spherical coordinates. So I'm going to do that because I see the two spheres. Sometimes it might be better to do cylindrical here, but when I see the two spheres, that just makes me think, okay, let's try spherical. Let's look at the region that we're dealing with here. So here's a picture of the region. So just sort of, there's a region plot 3D command in Mathematica. Let's see if we can make this a bit bigger here. There we go. So what you've got is you've got sort of, you can see there's sort of this inside sphere and then this outside sphere. And then this is really your cone cutting across on top here. And then you've got z equals 0 on the bottom. So you've got some region like this kind of a thing here. It's possible you do this in cylindrical, because if you sort of went from above, you would be able to describe, this is sort of r goes from something to something, but the issue here is that that r is going to change because you have this curve out here, but it may work out fine. I'm not going to do that, but you could try cylindrical if you want. I'm going to try spherical. So when I do spherical, what I'm going to get, I'm going to get triple integral of 1, that's the function I'm integrating. Now, spherical, the Jacobian is rho squared sine phi. And I have to give you bounds in terms of rho, phi, and theta. Let's see. So theta I can do on the outside, probably. And then rho and phi, let's maybe think about this z equals square root x squared plus y squared over 3, and see if that gives us an idea of maybe rho or phi, one is bounded in terms of the other. Here. So what I'm going to do, let's see, z, let's do this in terms of spherical. Z is rho, so z is rho cosine phi. Let's go back here. X is rho sine phi cos, whoops, said phi, rho theta, sine phi cos theta. Y is rho sine phi sine theta. One of the results here, if you put this together, x squared plus y squared is rho squared sine squared phi. So you can use the Pythagorean identities with the theta. This would work out, but this is just a handy fact to remember here. So get rho squared sine phi. And so what I get when I put this all together is z, that's rho cosine phi, is the square root of rho squared sine phi over 3. Could square both sides, get rho squared cos phi equals rho squared sine phi, whoops, rho squared cosine squared phi. Oh, except this should have been a sine squared phi in there too. Rho squared sine squared phi over 3. I multiply by the 3. Let's see, and I get, let's say I can cancel the rho squareds. I get 3 equals sine squared phi over cosine squared phi. That's going to give me square root of 3 equals, really this is going to give me a square root of these tangent phi. And that tells me that bound is phi equals, let's see, sine has got to be square root 3 over 2. That's going to be pi over 3. So I do some stuff. There's other ways to get here. But essentially, this cone is phi equals pi over 3. So I go back to my picture here. Let's see if I can rotate this the way I want. If I did sort of a straight up axis, I have to sort of go down an angle of pi over 3, and that's going to hit that cone. Essentially, that's what we're saying. So if you think about your phi here, that means you start at pi over 3. Now remember, phi is from the positive z, so it's going to start at pi over 3 and go all the way down to pi over 2. That's at the xy plane. So my bounds, turns out that it's really not going to matter what order we do these in. So phi, we just talked about, went from pi over 3 to pi over 2. We're in the first octant, so theta goes from 0 to pi over 2. Rho, this is radius 2, square root of 4, to radius 3. So we get 2 to 3. So those are really our bounds there. And now we just have this, this integral to evaluate, which should be relatively straightforward. So what I'm going to get is equals an integral from 0 to pi over 2, integral from pi over 3 to pi over 2. I'm going to integrate with respect to rho. That's going to give me, let's see, I keep the sign phi, rho cubed over 3, from rho equals 2 to rho equals 3, d phi d theta. That gives me an integral from 0 to pi over 2, integral from pi over 3 to pi over 2. I'm going to keep my sign phi, but let's see, 3 cubed, that's 27, minus 2 cubed is 8. That's going to give me 19 thirds, d phi d theta. So when I integrate this, so I'm just going to pull that 19 thirds out in front. I get an integral from 0 to pi over 2. Sine phi is going to integrate to negative cosine phi. I go from phi is pi over 3 to phi is pi over 2 d theta. So I get a 19 thirds integral from 0 to pi over 2. Let's see, phi of pi over 2, cosine pi over 2, that's 0. So I get a negative 0 minus cosine pi over 3 is a half d theta. So now this is going to be a positive 1/2. So I get 19/6 times the integral of just 1. It's going to be a theta. Let's just write it out. 19/6 integral 0 to pi over 2, 1 d theta. So that's 19/6 times the length of this interval, pi over 2. And my answer is 19 pi over 12. So you can calculate this through. And that really ends our video.